And here we are. That I always feel like it needs like the symphonic, the orchestra tuning their instruments to each other to lead everyone in to do this. So I'm Neal Davis. Ted Blackman is here for we're here for the final in the marathon week of Abet Developer Week experience live stream experiences for us.
That's right.
So this is the pattern not to be known as the engine pattern, as we are discussing today, where this came from. The blog post just went live that will be explaining the background and context for a lot of the things that we're going into here, and calling it the I've got it handy. Cool. So we're going to call it the nested core pattern, and maybe just start us off, Ted. Tell us what the nested core pattern is, and then maybe we can say why we're not going to call it the engine pattern.
Okay. Yeah. Well, the reason not to call it the engine pattern is just that I've never heard anybody call it that before. But we do talk a lot internally about nested core pattern or the Abet pattern, and the Abet pattern is a more specific. That's like a subtype of nested core pattern. So the nested core pattern is it sort of falls out pretty naturally as a way of organizing Hoon code, and it falls out of the general way that you stack cores in Hoon. So a core is a pair of code and data. The code is in the head, it's called the battery. The data is in the tail, it's called the payload. And any of the battery, of course, is a. We're going to mostly assume that you know this for the rest of this discussion, actually, that you know what a core is and the basic building block there. But I'll describe it very briefly. So, as I said, a core is a pair of code and data. The code in the battery is a set of knock formulas. So, any one of which can be run against the whole core as a subject. And so this is how recursion works in Knock and in Hoon. The core is the basic unit of organization of code in Hoon. You don't really see it when you look at Knock. Knock doesn't exactly know about a core other than the Knock 9 opcode, which says, basically, if you assume that you have a core, then find one of the arms in that core, treat that, copy it, treat that as the formula, and run the formula using the whole core as a subject. So that's
really just a consequence of Knock being homoiconic to some extent. Like it's just code and data look the same structurally until you actually force it to evaluate a particular cell structure or noun as code.
Well, yeah. So you can only do it because Knock is homoiconic, right? And so because your code and your data are both in the tree of the subject, all right, they're both in the noun and they're both represented as nouns. But if you just need basic sort of homoiconic execution, you can use the Knock 2 opcode, which does not involve cores. So if you want to use the Knock 2 opcode from Hoon, you can use the .tar rune, right? So if you're learning Hoon and you type in .tar into the dojo to run some raw Knock, that's the Hoon compiler emitting a Knock 2. But that's pretty much the only time that the Hoon compiler emits a Knock 2. The Knock 2 is very general. It says there are two formulas, so you have A, 2, B, C. So it says take the B formula, run it against A, the subject, to get a new subject, take the C formula, run against the subject to get a new formula, and then run that new formula against that new subject. So it corresponds directly to the S combinator in traditional combinator calculi. If that doesn't mean anything to you, it does not matter at all. But anyway, it says make a new function, make a new argument, run the function on the argument. Right? You can always think of a Knock formula, as a function that runs against the subject, and the subject is the argument. Now that argument normally is sort of the most complicated thing usually, right? The argument is stores all the data and all the code, right? So that's why we call it the subject, right? That's sort of where you store, that's everything that's in scope, everything that's in your environment. That's the subject. And yeah, so the way that we organize the subject when we're writing Hoon is by using cores. And so it's much more specific than just this knock2, right? So in knock2, you can say, run here, any formula, any subject, and just dynamically create some computation and run it. And that new computation that you create and run doesn't necessarily have anything to do with whatever you were sort of in the middle of or whatever is sort of in your subject right now. With a core, that's really not the case. It's much more structured. And in particular, what a core gives you that knock2 does not, well, it gives a few things. One is that it provides this pattern for recursion, right? Where it's like, okay, you put anything that you might recurse into in the head of your subject, right? So all the arms that you might fire while you're executing some formula against the core, all those arms are in the head of the subject. So that's one convention, right? So, okay, we're going to group them all over here. And then there's another convention for, well, and then the other thing is that the knock9 opcode has a static axis, like a static tree slot for which arm to fire, to say, where do I find this arm within the core? Which means that this is static dispatch. So it's much easier to optimize than dynamic dispatch, right? And so this is one of the reasons that, okay, knock isn't exactly fast right now. It's really not. But one can imagine having a much higher ceiling on how fast knock could go if you do some optimization work, because all of the knock that comes out of the Hoon compiler, unless you use a .tar rune, which is only used in very specific circumstances, has this dynamic dispatch. So whenever you fire an arm in a core, that's static. It has the static dispatch. So it's whenever you fire an arm in a core, that static dispatch, it's going from a fixed axis, a fixed slot within the tree. And so if you know something about the shape of your subject, then you can sort of statically analyze the function calls in a core much more effectively than with knock2. This also facilitates having static types. So we have a static type for the subject, and when you fire an arm, within a core and produces a result, the Hoon compiler can type infer across that arm to look at the result, and so that you know what the type of the execution is going to be. So basically, by constraining knock, which if you use knock2 everywhere is an extremely dynamic language where the basic control flow construct is eval basically, then if you just use that, then it's hard to do types, it's hard to do static analysis, it's hard to optimize, and so this is why knock has knock9 as what we call the function calling convention, right? Which says, okay, no, your code is going to be structured in this very particular way, where you have code on the left and you got data on the right, and that's going to be run in this particular way, where whenever you pull out one of those sort of stored procedures, the arms in the core, that will always be run against the whole core as a subject. So all of the arms are in scope, so they can be called using recursion, including mutual recursion. So cores provide a lot of convention and a lot of structure beyond the basic, which is like, is this thing Turing complete, sort of generality of knock. And then when we use, so getting back to the Abet pattern, that was the first step, is saying, all right, well, everything in Hoon is a core. And then the next step is to describe how cores stack or nest. And then we can talk about Abet as a particular way to use nested cores. Rabsef asks, define mutual recursion. That's where you have a foo that calls bar, and bar turns around and calls foo again, right? So recursion is just foo is calling foo, but if you have, they have them kind of go into each other, that's mutual recursion. So you can just do this with a core. And in fact, we do a lot and we don't usually think about it because it usually just kind of works. Make sure you cast the result types though.
So cores are useful because we have this discipline that kind of telescopes from a very simple core like a trap that doesn't even have a sample. It's a battery and it's a context essentially. And then we keep adding on layers of complexity. So we move to a gate and the various forms of gates. We move to a door, which is kind of like a gate that has many arms, and it can have samples at the outermost level, and it can have samples at each of the inner arms. And we're adding ways of stacking cores together to achieve the I guess I might call it the code discipline that we're looking for. That we're able to actually separate out the particular subtasks and the purity of the expression in particular cases. And so then what we're seeing here with the nested core pattern is we're just going sort of beyond the door to what's the next level of abstraction that we can use to contain different kinds of operations.
Yeah, that's right. And so I usually think of this in terms of scope, right? So whenever you stack a core on top of another core, which is of course that's how we do everything in Hoon, right? The standard library is a big stack of cores where you have one core at the bottom, and then you're prepending a new battery onto that, and then another battery onto that. And of course, any core there will have access to the original core. So when you stack a new core on top of an old core, all the arms in the new core, because the whole core is in scope, it's in the subject, all of those arms can also fire arms in the smaller core. And of course, when they do that, they'll do so against just that smaller core, right? So that when you fire the arm in the smaller core, it doesn't know anything about the bigger core. It's not dynamically scoped. And so that can be a little confusing when you're first learning it, but it's a very nice property. And then, so then, as you were saying, you might want to stack these cores in different ways. So the simplest way to stack cores is where you just have, Tisgar, Barsen, Tisgar, Barsen, Tisgar, Barsen, right, over and over again, and you're stacking just batteries. But then, so the standard library mostly looks like that. But then often you want to have some mutable state in a core. And so a gate or a door both have mutable state by convention in the sample slot. So in the head of the tail, right? So you have all of the arms in the head, and then the tail, instead of just being the rest of the core stack, is a pair of some mutable value and the rest of the core stack. And it's mutable basically that, this is how you fire a gate, or this is how you slam a gate in Hoon, is that you get the core, which is, you get the gate, which is a core and has the buck arm, and then it has the sample, and then it has the whole rest of the standard library or whatever else it was, whatever else the subject was when that core was defined. And then you swap out the sample with whatever the argument is, and then you fire the buck arm. Right? And so if that's any kind of core where you want it to be able to take in input, right? It's not just something where it has a bunch of helper routines that are sort of pure functional, but it might have sort of state effectively. In that case, then you need to have a sample slot in that core. And the thing is that then, as you mentioned, you can stack cores that have sample slots. So you can end up with multiple mutable slots. So the get by is sort of my go-to example here, right? So you have the by cores for dealing with maps, right? And so you say by of some treep data structure, right? Like a map. You say by of a map, and that gets you a core that has the map in its sample, and then has a bunch of arms like get, put, etc. In the battery. So then if you fire the get arm of that core, then you end up with a gate, and that gate wraps around that whole core. So the get arm is for looking up a key, looking up the value of a key in a map, and so that when you fire the get arm, that says, okay, that's going to produce a new gate that has in its sample slot the key that you want to look up, right? But then that's wrapping around this other core, the by core, that has in its sample slot the actual map data structure that you're going to be looking up the key from, right? And so you can swap the outer key with the, but to fire that, then, to slam that gate, then you replace the outer argument, or you replace the key with the actual key you want to look up. And then then you run the buck arm. And that buck arm actually, runs a bunch of other arms that are in the bicore. But that's fine, they're in scope. But you have these two sample slots that nest, right? So this is the other kind of, whenever this is always my go-to example for how to think about nested cores where you actually have multiple samples. And so this also corresponds to the idea of a closure.
I was going to say, should we pull up some actual code and take a look at this in practice?
Yeah, sure. Yeah, it's a good idea. Rabsaf asks, why is get by called with sensig, but you don't see that in nested core? Well, that's sort of by convention. You don't have to call it with sensig. Well, you sort of do. It's that's really for a door, right? So you want the sensig pattern is for a door. So you want to say, take some core, replace its sample, and then fire some arm after replacing the sample. And so when you can write a call to a gate the same way by saying, sig pal buck, core, and then argument.
So what would be a good one to pull up and take a look at here?
Why don't we look at get by?
Okay, that's in Hoon.Hoon.
Yeah. So this is the basic pattern. While you pull that up, this is the basic pattern for nested cores and for nested samples. But often it's the reason to do this is that you have something that's stateful, where you have something that's something like an agent, and that agent has state, and so that's actually maybe not exactly in its sample slot, but it's in another slot between that core's battery and its context. And in that case, when you have something, like an agent with state in it, then sometimes, you want to have, you want to define some basically like helper functions, but define them in line within one of the arms of that core. And so then you'll often end up with another inner core just inside of some arm, and the Barquette pattern is one of the, the Barquette rune is exactly for this. But then when it really gets interesting and where you need a bet is when that inner core actually gets called, has multiple call sites. So there are like different entry points, and each one of them wants to instantiate this inner core that wraps around the basic stateful agent core. So that's really when you want to get into Abet. But okay, so we have some code. Can you make that a little bigger?
Yeah, I'm messing with the fonts right now to make it as visible as I can. I'm actually trying to stick to the oh, weird. Now it's doing weird wrapping things. Sorry.
Are you using a non-monospaced font?
I'm using the new Abet monospaced font. It doubles up neighboring characters like their runes, which is kind of an interesting effect. And I'm not totally sure about it yet because it does weird spacing effects too.
What do you mean it doubles them up?
So you'll notice that it's single width on something like the G, or when I highlight a single character, like the lust, but when I'm away from it, it turns into a lust as a single width character. They become half width.
That's not going to work.
Yeah, it's kind of not.
That's what we call a non-starter. That is a deal breaker.
Working that great here. So
no.
Well, I thought I'd try the new font.
Just turns out it still needs some work. Well, any case, honestly, get is pretty hard to read without the skeleton. like I read Hoon very geometrically. It's much harder to read without clear indentation. There we go. All right, now we're talking.
I switched. Yeah, okay.
All right. So here's
Other than the fact that it's word wrapping key.
Yeah, ignore that, but that's fine. We want to start with the bar tar anyway, really. So here's an example. We're in the by core here, right? So the get arm is an arm in the by core, and so the by core has this sample called A. So the A is a map, right? It's an actual map, tree data structure, right? So it has N, L, and R, or it's sig. So as you see here, this is a gate that takes in B, which is a key, and then we are referring to both A and B inside of this arm. One should never blame Vim for anything. Right, and but this at least is a pretty direct way of seeing that when you have a gate that's produced by some arm that's in some core, then everything that was in scope for that core is visible to all the code that's in the body of that gate, right? So the body of the gate, here the gate is get, right? The core is by. A is defined in the by core. Get is defined as the sample of the get gate, and we can use both within the get gate, right? So this by core has closed around A. Or even if you just fire the get arm, and now you have a gate with a default sample, but you haven't replaced the sample yet, then that gate also has closed around A. So that's the idea of a closure, right? If you pull up, anyway, that's another one of those programming terms that you might know, and if you don't need to know it for Hoon. All you have to know is that this rule about this thing will still be in scope. Okay, so how are we doing with Vim and all that stuff?
It's visible. It works.
All right.
Just fiddling with it.
I was starting to.
I turned off word wrap, and it's a bit more visible. The problem, you run into interesting problems when you zoom in massively to teach.
Right. So the thing is that when you have, there are different ways of nesting cores, right? And so this just kind of falls out of the geometry of stacking things, right? So you have one core, and then you stack something with some mutable state and a battery, and then you stack another one with mutable state and a battery. And a way to think about this is, it's well, when do you why don't we just have get and by? Why isn't that just one gate, right? Why isn't it just get hep by and then set hep by or whatever? That would take in two arguments, right? It would take in the treep and a key, right? Why are we sort of currying it here, right? By saying, all right, well, you take in just the treep, and now you have this core, and then you can pass in other stuff later. And the basic answer is for convenience, right? So in this case, there are a lot of different arms that can fire, just based on the treep that don't have anything to do with one particular key. So it makes sense to group those, right? So that you say, all right, well, what are all the routines that just have something to do with this treep? And so you can think of that as so I think this can get into the Abet pattern. And I thought, Neal, you had a good example in the in that document you wrote up about Ames, right, where Ames has a map in its state, and so it has a map from ship to peer state. Well, ship to ship state, and typically that's a peer state. And yeah, search for Ames have state. We should see it. Yeah. All right. So here's the type definition. So this is the state of Ames, right? And it's got a bunch of stuff, but the only part of it that's interesting for us here is the first element in the tuple, which is the peers field, right? So peers is a map from ship to ship state. So these are all the ships we're communicating with, right? So we have a bunch of state about like, well, how many messages have we sent to this other ship? How many have they sent to us? What's the symmetric key that we're using with them? All that kind of stuff. So all that stuff is stored in the value, the ship state value for that ship. And so in Ames, we have one sort of general event handler core. It's called per event. And then within that per event core, there is a make peer core arm. And so basically there are a lot of different entry points to this core. Like there are a lot of different things that can wake up Ames where it has to do something. And a lot of those, in fact, the majority of those have to do just with one particular ship, right? So it's like, all right, well, we got a packet and it says it's from this ship. So it's like, okay, now we're going to go into a mode where we know we're going to be dealing with just that ship. And the vast majority of the time when we hear something from one ship, it has nothing to do with any of the other ships, right? And so what we do is we make it peer core to focus in on that one ship, that one peer, P-E-E-R, as in peer-to-peer. So we're saying, okay, we're gonna pin this ship and this ship state that correspond to that one key value pair from the map for this particular ship that we're dealing with. And we'll make that the sample of this peer core, which is going to be an inner core from the per event core. So why don't you pull up make peer core so we can see this. And while you're doing that,
we got it.
Rare Tapes says, this looks like if Scheme and APL had a little Iversonian McCarthyian baby. Yeah. Well, the data model is very similar to both, actually, right? So the noun, which is Abet's data structure, is very much like a Lisp data structure, just sort of made sort of maximally minimal. It's a strange phrasing, but like if you kind of strip away everything and the sort of what's the sort of primordial form of a Lisp data structure, you get a knock noun. And then actually APLs have a very similar data model. So APLs are also acyclic, and they you can represent APL data with nouns very easily, and we probably will. So I think you're probably even more right than you know, Rare Tapes. Anyway, here we are in make peer core. So this is the arm that's in the event core, and it gets past the peer state and a channel, right? So that's all the stuff that's related to this ship. And notice there are all these different arms in there. It's a big core because there are also many different entry points for this. So different entry points into the per event core. A lot of the times what they'll do is they'll say, okay, now I know I'm dealing with this ship. I'll go ahead and make a pure core and then fire this arm on the pure core, and some other event handler will, pull up, make it the pure core and fire a different arm on the pure core. And so, but basically, no matter what those entry points are, we make this pure core and then we throw it away, right? And then we go back to the event core, and we eventually actually throw that away and just return a list of effects and like the Ames core itself. So these are both ephemeral cores in the sense that within one activation of the Ames vein, you'll make an event core that will and then that'll make a pure core that's an inner core that stacks on top of the event core. And then those both go away by the time that Ames activation is over, and you're left with just the Ames state and the outer interface core for that vein. And so you need the Abet arm to get the results out of the inner core and propagate those results back out to the outer core. So basically, we make a pure core, we fire one of its arms, and then we call Abet to take the results back out and apply them to the event core. So, and you can see how this works. And it doesn't do very much, right? All it does is a put by, right? So it says her.channel there is the other ship. So that's the pat p of the other ship. And then we're just overwriting the value within that map to whatever pure state was in our sample there, right? So if we see that bar_t is pure state and channel, as the pure core, as any of the arms in the pure core are free to modify the pure state, and they're also free to modify the moves that are actually stored in the outer core, right? In the event core has a moves data structure. So if you look at the emit arm, right, you can see that it's basically just calling the outer emit arm, right? Ket emit, right, which just modifies the pure core that's inside of the event core. Remember, because the event core is stacked on top. I think I said that backward. Cool. The pure core is stacked on top of the event core, right? So from the pure core, you can modify the event core. And that's what's happening in emit, right? So in particular, we're just messing with the moves arm. We're just appending another move, right? Which will be eventually emitted. Those are the effects that get emitted as the result of this activation. But so when we call Abet here, the only things that sort of come out, right? We get a new modified event core. And that has modified moves and it has modified peers.aim state, right? And so this is a way of saying, this is the standard, right? We're defining the interface between the inner core and the outer core, where when this inner core is done, we always call Abet, and that propagates the changes to peers and the changes to moves back out to the outer core.
So why don't we walk through just real quick how this pattern is actually entered and utilized here. So we have make pure core. This is called somewhere from an outer core coming into this core. Well, I guess I should say that backwards. Anyway, we have this core. Let's say we come into update QoS, which is updating our connection status from a peer. And so the kinds of calls that are made in here are things like this emit call right here, which is different parts of this are referring to pure core, which is the subject of an arm is the core itself. So it's a handle to talk about the core that we're in. We're calling things like this emit down here, which basically puts a move on it receives a move and it puts a move onto our event stack. And then finally, when we come back and we pull Abet, whenever we're finalizing this, then we're doing this put by to modify the Ames state for each one of the peers and returning the event core and then kicking back out of the helper core here, the nested core.
Yeah.
Well, I guess these are options. These aren't both. No. This is a TIS.dot. This is a TIS.dot. Yeah. So both of these are happening here. Yeah.
Mm-hmm. Yeah, and the event core just says return, right? You can read that as return.
Yeah. The thing that cues anyone in that they're reading nested core pattern in this sense is the presence of Abet. Like that's the universal across all of these is Abet.
That's right. And that's the reason that it's called Abet is that we wanted something that's using typical Abet naming, right? Where we want something that is sort of evocative of what's going on, right? We're kind of aiding and abetting the outer core with using the inner core. But there is no name for this in traditional computer science, right? And we could say, and it's also not, it's not too specific, right? It's just, here's the thing you want to look for. Do you see an Abet arm what is an Abet arm? It's like, well, it's this thing for doing this procedure, right? And that's sort of the only name it needs.
Now, the first time that I ran into this was in user space applications, where these are used to build lists of event cards for Gall agents and then flopped back out at the end whenever you do the event resolution coming out of this core.
Yeah.
And then here we're looking at something that is, deep inside the kernel. We're looking at Arvo. It's present in Clay and Bane and Gall. Bane actually is interesting because it has a different pattern, a different way of using this, where the adjunct core is not actually nested. It's adjacent in a sense, but you see this applied a few different ways. But in user space, what are the kinds of ways that we're seeing this used besides what I mentioned with Gall move handler?
Well, I don't know. I don't do too much user space, but actually there was a
fair enough.
Well, actually I worked on Kiln. So the current version of Kiln, which is soon to be removed basically by the upgrade overhaul work that Philip is doing right now. And good riddance. It was not my finest code. But in that Kiln has, it does have an Abet arm that's pretty similar. It's also for a map because Kiln maintains a mapping of desks to desk state, because this is the part of the system that tracks which agents are supposed to be running off of which desks and where those desks are supposed to be synced from. So yeah, if you look at the VATs, yeah, that's the one. Okay. Yeah, so that and if you notice what that Abet arm does is it returns Kiln with its arc replaced by overwriting this one key value pair, right? Same pattern as Ames, right? So the Kiln core is the outer core. VATs is an arm within the Kiln core. We get past, this is it's a slightly different structure here, right? Because instead of a gate that produces a core, it's a door, right? It's a bar cab. But we're literally here, you can see it even a little bit more clearly here, right? We're past this one key value pair, the desk and the AROC. That's the key and the value from the ARC map. And so then, we are, again, just modifying, we're returning an outer core, right? The Kiln outer core with its state map modified with this one particular key value pair overwritten by, by the results of messing with the value in the course of running some arms in this inner core. And this also does propagate the moves outward. You don't see that here, but this can also emit moves. Kiln has also a moves data structure inside of it, some list of moves. And you can see that with the emit arm here, which does the same thing, right? It also says, hey, take your, overwrite the outer core that's inside of the inner core with the result of calling ket emit, right? So the emit arm from the outer core, not the inner core. And which actually brings me to something that it can get confusing when you're talking about this stuff. So when I say inner core, I mean the head of the core stack, the top of the core stack. That's the inner core.
The thing that's closer to the Hoon subject.
Yeah, closer to the root of the subject.
Yeah.
Yeah. And because the whole thing's in the subject, right? But that peak of the subject, the top of it, yeah, that's what I call the inner core. So if you look at it as a tree, right? It's the outside of the tree, so it's a little confusing. But it's the inner core in the sense of it's the inner scope, right? So Hoon is lexically scoped, which means you can tell what the scope is by reading it. It's not dynamically scoped, and so the inner core is indented. So that's how to know which one's the inner core, is the one that's indented further. So if you ever get confused, that's how to think about that. But yeah, the inner core, somewhat confusingly, does contain, as a tree, right? The tree of the inner core does contain the outer core in its context.
Well, this is a good example.
It's a subtree of the inner core.
This is a good example where other things would do naming conventions, like rather than this, they would prefix it with a 2-letter.
And I should have done that. It was a mistake not to, and it caused us some problems actually. Sorry. Live and learn. I've come to really appreciate. I've come to really appreciate the va, hep, emit pattern, like that style of naming, because because then you can typically the way to find anything in a Hoon file is you grep, or not grep, but you use a vim search, right? So you typically just search for whatever you're looking for, and so if you search for emit, and then there are 2 or 3 different arms called emit, then it's hard to know which one you're in. So prefixing them with the standard is to use a 2-letter prefix describing the core that's inside of. That's a very nice. That's quite a nice pattern. It looks a little funny when you first see it because it looks kind of cryptic, but then once you get used to reading it, it helps a lot.
All right, let's see. There's other patterns, instances of this in clay. Do you want to talk about the Ames versus the clay style breakdown? That might be helpful for people looking at this.
Why don't you describe that, and then I can chime in.
Okay, so my understanding of this is that Ames style nested core pattern modifies one part of a map, one key value pair. Like it's sort of laser focused on adjusting one thing in particular. And clay style nested cores do that, but they may stack together a lot of other effects as well. They're sort of less pure in a sense. I mean that in not the mathematical formal programming sense, but they may do more things than what an Ames style nested core pattern does. So the Ames style nested core pattern tends to be easier to read for someone coming in from outside the code, and the clay stuff tends to be look a little more tangled.
Yeah, I think the difference there basically is, and it may be unfair to clay to call it that, but the difference I think is that sometimes, despite having one particular key value pair in focus in the inner core, you may also modify other key value pairs while you're at it, right? And so the Ames style says, well, we're only going to do the put by on this one key value pair, which is sort of implying that you're not going to do that with other ones, but you could actually, right? There's nothing that prevents that. And so, but you have to be careful if you're going to do that, because then you basically have a leaky abstraction, right? Where you're saying, all right, well, I'm going to be, within this inner core, I'm going to be modifying this one key value pair. But then you actually go and modify a bunch of key value pairs. And so the abet just sort of applies to one. And often what you'll end up doing is you'll be calling abet, you'll like instantiate a sort of somewhat different version of your own core, or you'll just call abet on your own core after modifying one of the other key value pairs, right? So you're kind of telescoping, but you're kind of telescoping sideways, which feels weird. So you can do it, and there are times when you probably should, because that can be a lot more concise.
And this is the way that Gall
do that.
This is the pattern that Gall follows as well, where it has a move handler core, and it has an agent handler core that sit side by side and kind of call into each other. And so
that's an abet pattern also. The app core, which is the per agent core, is very much an inner core inside of the mo core. And that focuses in on one agent name and agent state key value pair that's in the, I think it's called yokes, Y-O-K-E-S. There's a map so Gall stores a map from agent name to all the state that it's tracking for that agent, including the actual agent core itself. So the mo core is the general like per event core, right, per move. And then, as soon as we know, okay, we're going to be dealing with this one particular agent, then we make the app core for that agent, and then that has an abet. And it only ever modifies that one agent and the mo core itself, but it never overwrites any of the other bindings there, like any of the other key value pairs. So I guess that's the Ames style as well.
Here's RAPSF. I think RAPSF is going to stick with the engine terminology. The engine terminology.
Maybe it'll stick.
I should address this. So the engine pattern is what I've heard several non-core developers call this usage, and I'm not exactly sure what the origin of calling it the engine pattern is. Ted tells me that Curtis suggested renaming doors to engines when he was leaving, but this didn't catch on. So,
yeah, that's the first time I've heard the term engine used in Abet. Yeah, it was as part of a style guide recommendation that Curtis wrote as he was leaving years ago, and most of which we have not adopted. Some parts of it, but yeah.
Well, I think we're going to pry
proposal.
We're going to pry engine from RAPSF's Cold Dead Fingers. So it's a Quartus term of art. I think that's fine.
Well, but what he's saying here is interesting, right? He's saying he thinks engines are good for integrations with other agents. It's like an in-agent library. I actually don't entirely understand what you mean there, RAPSF.
Well, we can't bring him on. He'll have to type quickly if he wants to follow up with that.
Yeah.
But I have noticed that Quartus has been using the nested core pattern in several of their agents, so they are getting used to employing this stacked pattern.
Yeah, I do highly recommend using the nested core pattern. You never have to use it. And you can misuse it as well, because basically you have, you can turn this into mutable global state, despite Hoon being a statically typed functional language, right? Like you can actually build something that works a lot like mutable global state. If you have, some core with some state in it, and then you have all these inner cores, but they can still modify the state in that outer core. And so, you do have to sort of be judicious about that. Like, that's why typically we only overwrite, one key value pair in the Abet, or just the key value pair, and the moves data structure, right? That's a very common pattern that you're kind of in-queuing effects throughout your whole program. And so even when you're in an inner core, you might just directly in-queue effects from right there, because there's no need to sort of have those go through some layer of processing if you don't need it. So it's possible to misuse it, right? If you have things that are sort of too, it can get really hard to read and hard to reason about if you're sort of jumping across, right? If you're changing a lot of state that's sort of deep in the core stack, and sort of jumping into different cores from inside of other cores, you can mess that up. And the way you mess that up typically is that you forget that you've changed contexts, or you forget to propagate changes that were made in an inner context back into an outer context, right? So with an Abet, if you do it right, then there's very little risk of this, because you've kind of constrained yourself to only modifying a small piece of that outer core. You're sort of only doing it once. You're not going to jump sideways. As soon as you start jumping sideways, meaning like from inside the inner core, you instantiate another inner core that has a different key value pair and focus, then it's really easy to mess it up. So I highly recommend avoiding sort of jumping sideways or doing anything sort of interesting there. You can, and there are times when that can make for a really concise, highly recursive algorithm. And
it's like go-to.
Maybe. I mean, firing an arm in a core is very similar to a functional go-to. Mm-hmm. And that's part of why it's powerful, right? And so sometimes, you can actually you'll sometimes see this where you just have a tis sig, one arm, another arm, another arm, right? Where you say, just do this in a row, right? You can do that. And there are times when that's appropriate. But yeah, it's because like anything powerful, you have to be careful with it, right? And so it's one of those things where if you stick to the conventions, you'll be in good shape. And that's a lot of what the conventions are for. And then, yeah, if you need to do something more exotic, then yeah, you can. So some of the like the ordered map, some of the ordered map traversal code does sort of use ARM firings as go-tos, and that's convenient for that. But yeah, but the reason I would say that it's good to use the nested core pattern is that it is more concise than other ways of structuring code, and it's clearer. And it's a very natural way of representing complex programs and breaking them up into different sections that have different responsibilities. So it often very cleanly maps onto the problem space, especially if you have something like Ames or Gall, right, where you have this mapping, and then you want to do complex, stateful, and effectful computations within that focus in on some part of that mapping, but in a way where they're still sort of part of the overall structure and have access to these more global variables that they can read. So I would note that actually there's no one has formalized any of the math around this nested core pattern, but I've suspected for years that it is basically comonadic in nature. So a comonad is just a comonoid in the category of endofunctors. What's the problem? But it's actually pretty different from a monad in terms of the way you use it. And there are also many of them the way there are many monads, but basically comonads have to do with you have some sort of data structure or some sort of context, and then you want to make a cursor within that context that points at some smaller piece of it. And so then you have access to the cursor and the broader context. And you can nest those. So you can have, a big broad context and a slightly smaller one, and then a smaller context on top of that. And you still have access to all of them. And that's very much the idea of the nested core pattern. So I suspect there's something comonadic in there. Maybe the mathematicians will figure out a way of using that to describe it in the future. There's some good posts on Haskell for All blog about comonads and how they relate. And I think that if you read some of those, there's one about object orientation and how objects are comonadic. That one, you'll look at that and you'll think of cores and firing arms on cores.
Now, there was a comment you'd made to me about being able to use the nested core pattern to build a stateless library. Can you expand on that? Is there a good example of that you're aware of?
Yeah, the standard library, I would say. Right. So, the Hoon.Hoon has five chapters, or like 5 cores that stack on top of each other. And so the first one is like basic arithmetic. The second one is containers, lists, maps, sets. I don't remember what's in the third one. And then the fourth one is parsers, and the fifth one is the Hoon compiler, roughly. Each one of those builds on the previous one, right? So in order to do maps and sets and lists, like it's helpful to have the arithmetic. It's not just, I think there's some other containers in there too. But in any case, you kind of want very basic arithmetic as the base layer of your system that you can then use for everything else. And then, for doing anything complex, you need containers, right? Meaning container data structures, right? Algebraic data types. Or they're implemented as algebraic data types. And then you also want so then you need to layer things on top of that. And so that's a good pattern when you're building libraries. Often it's not the only pattern, but that idea of a stack of layers, you can implement that very directly with a stack of Barsen cores, right? And you only need stateful cores if they need, or you only need a sample slot if there's something stateful there, basically, or something where it needs to receive input.
How does that differ from a standard library import, though? I mean, if a faceless is importing a core that isn't, doesn't know about your code.
Yeah. So, right. So that's a different way of structuring it. So that's not a strict stack. That's a tree of imports, right? So, where basically each layer has a tuple of imports, and each of those can have a tuple of imports, right? All sort of terminating in the standard library Zeus. So when you fasless something in a file that says build the rest of this file after prepending the result of building this other file to the subject, right? So if you just have one fasless, or if you have no faslesses, right, and you just have some Hoon file, right, and it doesn't have any imports, then Ford will build that against Zeus, the standard library, as its subject, right? Just Zeus. So it says, okay, Zeus is a standard library. Like, all right, here, like, we'll take this Hoon, we'll compile it against that, right? So everything that's defined in Zeus is in scope for your, right? It's in the subject for your file. And typically, what your file will do is it'll wrap some core around, like, it'll stack some core on top of the standard library, right? That's what almost all files do. Maybe it's a bar-send core that's defining a helper, a bunch of helper functions in a library. Maybe it's defining an agent core, but whatever it is, it's going to stack right on top of that standard library. But let's say that you want to import some library, you want to import libshu, right? So you do fasless shu. When you do that, then Ford says, okay, go build shu, however that needs to happen. Take the result of that and prepend it onto the subject. So now you have a pair of shu and Zeus. So now you have a pair of cores, typically, right? Because most of the things you're going to be importing are cores. So typically you'll have a pair of cores. And if you import a few things, right? If you've had, say, fasless debug com shu, then it'll prepend shu, and then it'll prepend debug. And now you have a tuple of 3 cores as your subject. And so this works cleanly because even though each one of these cores actually has another copy of the standard library stack inside of it, that's fine because they're just, it's just a pointer, bro, right? Like, you're just copying pointers to the standard library. So you're not duplicating the memory. And you have very fine-grained control over the variable naming and the scoping there. Right, so you can have each one of those have a face wrapped around it, so it doesn't expose any of its internals. It doesn't shadow anything that comes behind it in the tuple, or not. You can have it shadow if you want, and sometimes you do want that. And that just depends on whether you import it with fasless shu or fasless tar shu, right? So tar shu says import all from the shu library without putting the shu face on that. And so then if that does shadow the standard library, then it does. But if you put the shu face on it, then it doesn't shadow anything from the standard library, other than if the standard library had something called shu in it, which it doesn't.
Yeah, that's you can always get in trouble with shadowing in Hoon.
You can, yeah. But it's at least it has a very principled approach to it, though. So you can sort of deal with it however you'd like, and it's purely lexical. The variable, the symbol resolution is just purely left to right across your tree, right? And so that's how you know the answer of, like, well, if you have 2 things named shu, if I just write shu, which one's I going to refer to? The one that's on the left, right? So this is why you should always know the geometry of your Hoon programs. One of the many reasons to always know the geometry of your tree.
All right, we're at about an hour, so we're going to have to wrap this. I dropped another link to the blog post that introduces and explains some of these ideas. This has been used. This pattern has been used obviously everywhere in the definition of Hoon and Arvo, but now we are officially exposing it to the world in a way beyond just read the source code.
Okay. Yeah, thank you for bringing this to people's attention. I think it's a good thing for people to know about, and it's an important aspect of structuring more complex Hoon code.
All right. Awesome. Thank you. And well, there's requests to continue these kinds of chats on Fridays. We'll see about that. That's a good idea.
That's a good sign. All right.